So far in acid-base chemistry, we've calculated the pH of strong and weak acids, diprotic acids, strong and weak bases, and salts. This time, we want to discuss the pH and action of buffers. If you remember, a buffer is a solution that contains something that prevents the pH from changing even when you add a strong acid or a strong base. This is what blood is. Blood is a buffer so that the pH remains constant as close as you can within experimental error. Now, what we want to do is discuss buffers today, but obviously, if you have something that you want to soak up acids, it's going to have to contain a base because that's how it works. And if you want something that's going to soak up a base, it has to contain an acid. Buffers contain both an acid and a base, but they have to be chosen very carefully and correctly. And buffers are based on neutralization reactions to soak up the acid and base that you add. So the first thing we need to do is that chemists have divided neutralization reactions into types, and we want to look at those types first. Just like any time we use type numbers in this class, you don't have to know the type number. This is just for classifying for us, but I want to call this first type of neutralization a type 1, where the acid and the base you're mixing are both strong. This is a very typical one. You've probably studied it other places. And I'm going to take the classic acid HCl and mix it with the base sodium hydroxide. And you know that when you mix an acid and a base, you get a salt plus water. What I want to do is show in this discussion that it is possible to use weak acids as part of a buffer, but not strong ones. And we're going to discuss that by showing what happens in these different neutralization reactions. This is what a strong acid looks like, sort of, if you draw it out. I put these 100A minus and H plus ions in solution because this is a strong acid is 100% ionized. As soon as you put a strong acid in solution, the pH goes down to the maximum extent it can because all of the H pluses are released in solution. The only H pluses that change the pH are ones that are not attached to anything else. And in the case of strong acids, that's exactly what happens. They're free in solution. To look at this reaction ionically, HCl splits apart 100% into ions, and so does sodium hydroxide. The only two ions that can do anything are the H plus and the OH, and they will come together to make water. In this diagram, I show the OH up in the upper right-hand corner, and you can see that it's very easy for the OH to find an H plus to react with because they are all over the place, and so the OH is just going to snap one up. And after the H plus and OH react, all you're left with in the beaker is the water that's formed and the two spectators, which is sodium and chloride. And if you boiled off the water, you would see the sodium chloride salt. The net ionic equation for this is just H plus reacting with OH because the other two ions are spectators. If you split the ions apart, you can see that HCl, NaOH, and NaCl all split apart, but you're not going to split apart the water because it exists as molecules. And if you cross out what's the same on both sides, those are the spectators, and you end up with the net ionic that I have written there. The goal of this discussion is for you to be able to easily write the net ionic equations for each type of reaction. And as we go, I'm going to show you how to do that from scratch, but then I'm going to show you a simplified method to do it later. One of the things about a strong acid, strong base reaction that's important is that the salt you get is always of the type we classified as a neutral salt. In this reaction, for example, Na comes from group 1, and so it's neutral, and Cl, of course, comes from a strong acid because that's what we're doing, strong acid, strong base, and so NaCl ends up being a neutral salt. This is going to be important later when we talk about titration curves, which we're going to do at the end of the next class. Now this diagram just shows that if you change the spectators in this, it's not going to change the net ionic equation because it's just going to give you a different salt. Whatever the metal is connected to OH combined with whatever the negative is connected to H. Even in those kind of reactions where you have barium and strontium hydroxide, which have two OHs on them, I want to show you that even though with the two, it doesn't change the net ionic. In this case, in order to react with the OHs, you need two HCl's, one H plus for each OH, and you end up with 2 water. Barium chloride is still a neutral salt, so let's split the ions apart and see what you get for the net ionic. When you split the ions apart, you get 2H plus 2Cl minus, you get a barium and 2 OHs, you get a barium and 2 Cl's, and you keep the water together. So when you cross out, you end up with 2H plus 2 OH and 2 water, but since it's a 2 in front of everything, you can also reduce the 2's, and the net ionic comes out the same. The time when it gets interesting is when you start using weak things. And in this reaction, I'm going to use as the weak acid acetic. So when we mix acetic acid with sodium hydroxide, this reaction doesn't really look any different than the type 1 yet. An acid and a base gives you a salt and water, but I want to show you that this is going to demonstrate why it's possible to use acetic acid as part of a buffer, but you can't use a strong acid like HCl as part of a buffer. If I were going to draw a picture of the beaker that's showing what's in a solution of acetic acid, you already know that when a weak acid dissolves in water, it's going to be mostly molecules. There's only going to be a little of the ions. So I tried to draw a diagram of a weak acid. You can see that in this acetic acid, the H's are all stuck to the acetate except for one. In the bottom there, the H plus and HA are separated, but only about 1 out of 100, because you know weak acids only split apart about 1%. That means that most of the H pluses cannot affect the pH because they're still stuck to the acetate. The only one that makes the pH go down is the one that's split apart. And that's the reason why weak acids do not lower the pH anywhere near as much as strong ones, because most of the H's stay stuck. And we're also going to see that because the H's can stay stuck without changing the pH, those H's in a weak acid serve as a kind of a storage form of H+. In other words, if you put OH in here, the OH can only react with the H+ that's free. The others are still stuck, and so the OH doesn't change the pH much when it just reacts with that one H+, because the others are still stuck. If you write a net ionic equation for this, you don't want to split apart the acetic acid because it's 99% molecules, and you'd rather write it the way 99% of them are than the way 1% of them are. So the sodium hydroxide and sodium acetate split apart, and the water does not either. So this time, all you have is one spectator, the sodium. And if you look at the net ionic that I wrote down at the bottom of the page, doesn't it look like the OH is pulling an H directly off the acetic acid? I'm going to show you that that's not exactly what's going on, but if you think of it that way, you can think of it as that's the final result of the process, and that's how OH neutralizes a weak acid. When I write acetic acid, then in a beaker, I'm going to write it as mostly the acid because it's mostly molecules, and there's only a little bit of the ions. The sodium hydroxide, though, is still completely dissociated. This is a diagram of the OH being added to the weak acid, and the OH cannot pull an H actually directly off the A. It can only react with the one way at the bottom that's free, and so it's going to take a lot longer for it to be able to get to the H+, but it will react with the H+, because eventually they'll find each other. As I said, when we looked at the picture, the OH will eventually find the H+ that are there, but it can't react with all of them because most of them are stuck. So what has to happen is for the OH to react with the H+ that are there, but then you have to wait for more H+ to dissociate before it can react with more of them. Here I'm showing acetic acid splitting apart. When you add OH, it will react with the H+ to form water. That, in effect, is like eating the H+, so you're removing what's on the right of the equilibrium. So according to Le Chatelier's principle, you're going to shift to the right and produce more H+. Then the OH is going to react with that. Again, you eat the H+ that has come off, and you shift to the right again to produce even more. What this does is it actually produces a kind of a two-step cycle. In the first step, the OH neutralizes the H+ that's there, but then more of the acid has to ionize in order to form more H+. And then it can neutralize it again, and it goes in a circle. The time when the reaction stops is actually when all of the acid is completely gone, because the acetic acid is the source of the H+, and once it's gone, you can't get any more. So what you see left in the beaker when you're finished, the acetic acid is gone. The H+ and OH have made water, and the other two ions make up the salt. So at the end of the reaction, you still end up with a salt and water. And that's what the net ionic is showing. Even though it looks like the OH is pulling the H directly off the acid, it's actually this two-step cycle. You don't really need that much to know about the cycle, but if you think of the OH pulling the H directly off, for buffers, you're fine. And if you look at the salt that forms, sodium acetate would be classified as a basic salt. Sodium is still neutral from group 1, but acetate is the conjugate base of acetic acid, and it's on the right of the arrows in the Ka table, which makes it a weak base. So sodium acetate is a basic salt. A type 2 neutralization always gives you a basic salt. So you can see that the difference between the type 1 and type 2 neutralization is just Very simple. In the type 1, the negative ion is not present because it's split apart as 100% ions, and it's also considered one of the spectators. But in the type 2, it's not. And what you do then is, the idea is, this is the reason why weak acids can serve in a buffer. We already know that the H that's attached to the acetic acid cannot change the pH. But in the case of a strong acid, all the H plus comes off immediately, and so none of it is stored. And here, just as we showed before, this is the slide that shows all the H plus already separated from A minus, so that the pH has already decreased to the maximum amount possible. So the weak acid, as we said, is storing H pluses for the next time you add OH. The pH doesn't really change that much when you add a little bit of OH, because all it does is react with the H pluses that are there, and the rest of them stay stuck. But in the case of a strong acid, the H pluses are all present in solution immediately, and none of them are stored. The pH has already changed to the maximum extent. Now, any of the weak acids in your Ka table can serve as a part of a buffer. And those weak acids also include the ones in the diprotic table on page 10. I'm going to show that later. In the general form for a type 2 neutralization is where, as you can see, the HA representing any acid, the OH pulls the H off and you're left with a negative ion. And I showed you some specific examples of this with acids from your Ka table. You can include NH4 plus as one of the weak acids because it is a weak acid from the left of the arrows. The OH still pulls an H off of NH4 plus to give you ammonia. The difference is that the ammonia that forms is neutral rather than a negative ion. Now we want to look at the type 3 neutralizations where you switch. You use a strong acid and a weak base, and I'm going to divide the two types of weak bases into neutral ones, which I'm going to call type 3A neutralization, and anions, which are type 3B. Ammonia is the only neutral one that we look at, but in organic, there's all kinds of them, and almost any compound that has an N in it can be a base. And so I want to do this because of the salt that forms in the reaction with ammonia, and let me show that. If you mix HCl with ammonia, you can almost tell what's going to happen. The NH3 is a base that wants to accept H pluses, and you have 100% H plus from HCl, and therefore one of the H's is going to stick to the NH3 and form NH4, and then you'll get the salt NH4Cl. Most of the time we run these reactions in solution, and you really can't see what's going on because you have clear solutions to start with and clear at the end. Sometimes it'll get hot or smoke a little bit, but this one you can run in the gas phase and show that it actually works. If you take concentrated HCl solution, there is HCl gas above it, which is in equilibrium with the solution, and the same with ammonia. If you take concentrated ammonia, there's NH3 gas in equilibrium with the solution. If you mix the two gases, you can actually see the ammonium chloride form in a reaction. And the next slide is a picture of that someone did in the lab.
We're going to look at an acid-base reaction between HCl gas and ammonia gas. There's still a transfer of a hydrogen ion from the acid HCl to the base, ammonia, it will produce ammonium chloride, which is a solid, which we'll see as smoke coming out of the tube. I'm going to add some concentrated aqueous ammonia to one of the flasks. We're going to add some concentrated hydrochloric acid to the other flask. Most of our studies with acids and bases are going to be in solution, but you do not need to have an aqueous solution to have an acid-base reaction.
If you write the net ionic for this one, the only spectator is really Cl-, and when you look at the net ionic, what it looks like is that the H+ is just slapping on to the weak base. If you think of it that way, it's fine. I'm going to show you that it is a two-step cycle, but why is the H+ then neutralized? Because remember, whenever H+ sticks to anything, it can't change the pH because it's no longer free. Now, in order to show the two-step process, you have to understand what NH3 does when you put it in water. And we've talked about this a lot. NH3 actually pulls an H off of water about 2% to form OH. So I drew the NH3 in solution as mostly NH3, but there is a little NH4+ and OH. And the HCl has the free H pluses in the same position as OH was in the type 2. The H+ is able to react with the few OHs that are present. And after that occurs, you have to wait for more OH to be produced from NH3. So the H+ is going to react with the free OH to make water, which eliminates the OH from the right, and so by Le Chatelier's principle, you have to shift to the right and produce more OH. Then the H+ will eat that OH, and when you eat that OH, you have to shift to the right again. And this process continues as a two-step cycle, just like in the type 2. The H+ is neutralizing the OH, and then more NH3 gives you more OH, and then H+ neutralizes that. This reaction stops when the NH3 is completely gone because that's the source of the OH. So therefore, when the reaction is over, all you're left with in solution is the water that formed. The NH3 is gone, and you also get the salt, ammonium chloride. So again, for this type of reaction also, you end up as the products being a salt and water. But this time in the type 3A, the salt that you form is acidic. Ammonium is an acid, and so it makes acidic solutions. So in the type 1 reaction, we got a neutral salt. In the type 2, we got a basic salt. And in the type 3, we got an acidic one. And this is going to be important when we discuss especially titration curves. Now suppose that you want to, instead of mixing a strong acid with ammonia, you want to mix it with a negative ion. The only difference is that if you use one of the negative ions that's a weak base from the Ka table, you have to put a spectator with the negative ion in order to get it to dissolve in solution, because you can't have just the negative ion by itself. So if you wanted to mix HCl with Cn-, you have to put a spectator with the Cn- to get it into solution. I'm just using potassium, but any positive ion from group 1 would work. What happens is basically the same thing that happens with ammonia. The H+ from the HCl sticks to the HCN. I'm sorry, sticks to the CN minus to form HCN. This time when you split the ions apart, you don't split the HCN because it is molecules, mostly 99%. So when you cross out the spectator, there's an extra one, K+, but the net ionic equation still looks like the one for NH3. It's just that the H+ basically slaps onto the weak base and gets neutralized because now it's stuck. You can also use any of the negative ions in the Ka table on the right for the base to be the weak base. So the general form of that is just H+ sticks to the weak base. If it's ammonia, I called it type 3A. If it's a negative ion, I called it 3B. The reason I split them is because the 3A produces an acidic salt. The 3B really doesn't make a salt because HA is neutral and you can't combine it with anything else. Now theoretically there should be a fourth type, which is where both the acid and the base are weak, but this is not really even a neutralization, because if you mix a weak acid and a weak base, the acid doesn't really want to lose the H and the base really doesn't want to accept it, so they kind of just sit there. There's nothing that really happens. It is only a neutralization if one or the other of them is strong. We also talked about a type of salt called a mixed salt, where NH4 is a weak acid and the negative ion is a weak base. There's really nothing that goes on here either, and so we didn't do any pHs for those kind of salts, and we're not going to also do anything because the reaction of a weak acid and a weak base is not really even a neutralization. Those two-step cycle problems kind of look complicated, and you don't really need to be able to analyze all that in order to write net ionic equations for these neutralizations. I want to show you a simpler method, and this is how it works. If you want to write a strong acid, you write it as H+. That's what we've been doing all semester, so that's no surprise. And if you want to write a strong base, write it as OH. That's the only real strong base in water, so you definitely want to write it that way. If something is weak, you just write it the way it is. It's not forming ions, and so you just write it down as it is. Let me show you how some of these work. In the first example here, let's suppose you want to write the equation for the reaction between a strong acid and a strong base. How would you do that? Well, you write a strong acid as H+, you write a strong base as OH. If there's anybody that doesn't know the product of this reaction, that is a very bad situation. It's obviously going to form water, and the salt you get in this kind of neutralization is neutral. Let's suppose you want to write a weak acid strong base. You write the weak acid stuck together, so I wrote it as H plus anything. That's our weak acid. You write the strong base as OH. And what happens in any of these is that you can think of it as OH pulls the H directly off the acid to form water, and the negative ion is left. This is a reaction that gives you a basic salt. If you use ammonium as the weak acid, it's the exact same reaction. OH pulls off an H+, but the ammonia that you get is neutral, and so you don't really get a salt. If you want to mix a strong acid with ammonia, this is the kind I call 3A. You write NH3 as NH3. It's weak. It doesn't do anything. Write it as it is. Whenever you see this combination, all you do is slap the H plus onto the base. And in the type 3A, you get an ammonium salt, which is an acidic salt. If you mix a strong acid with a weak base that's negative, they're still going to slap together. It's really the same reaction again. But this time, because the HA is neutral, you really don't get a salt. What I want to do at this point is do some actual practice ones using real compounds mixed together. I'm asking you to write the neutralization reaction that forms or that occurs between these two substances. The first thing you have to do is classify each one and then decide what happens. HClO4 is one of the 6 acids that's strong, and strontium hydroxide is a strong base because it's a metal plus OH. So you write the strong acid as H plus and the strong base as OH, and they form water. You don't have to know the type number, but I put it there so you can look back in your notes. And you also don't have to write anything that's a spectator, because all we want is the net ionic. And we showed that even though there's 2 OHs on the SrOH2, the net ionic still has 1s in front of everything. Now let's suppose you want to do HBr and KF. You have to classify them. You know that HBr is one of the 6 strong acids, but how are you going to classify KF? You know that the K is neutral because it's in group 1, so it's really the F minus that's going to be the important thing. Because F minus is on the right of the arrows in the Ka table, it is a weak base. So KF is actually a basic salt, but the important part of it is the F minus. So the K really acts as a spectator, and you're only going to worry about F minus. You write the strong acid as H plus and the weak base as F minus, and whenever that happens, they slap together. And that's the net ionic, which is officially a type 3B. I can write either the acid or base first. So in this one, writing the base first, I'm going to mix ammonia and nitric acid. Everybody by this time knows that ammonia is a weak base. It's on the right of the arrows in the Ka table. And you also know that HNO3 is one of the 6 strong acids. So when we write this, we're going to write the NH3 because it's weak. We just write it as it is. You write the strong acid as H plus and let them slap together. And this is officially a type 3A. Here's one where we're going to mix NaOH and HCHO2. You know that sodium hydroxide is a strong base. What about the acid? This is formic acid. It's in your weak acid table. So you're going to write the strong base as OH, and you're going to write the weak acid stuck together. And in these kind of problems, the OH pulls off the H to make water, and you're left with a negative ion as well. This is a type 2. Now, problems where I give ammonium something as one of the reactants is always a problem for people, but please remember that anytime I give you an ammonium salt, the ammonium is always going to be the important thing, because the other ion is going to be neutral. It comes from a strong acid in our problems, and so you pay attention to the fact that the NH4 plus is a weak acid. I keep showing this because people tend to forget it. Here's the ammonium on the right of the on the left of the arrows in the Ka table. So since NH4Br is a acidic salt, but the Br minus is really a spectator, you're going to write it as NH4 plus. So you write the weak acid stuck together, you write the strong base as OH, and the OH pulls an H off. So you get NH3 in water, and this is actually a type 2. The next problem is HClO2 and barium hydroxide. You can see that HClO2 is a weak acid by looking in the table. Here it is in the Ka table. Barium hydroxide is a strong base. So we write the weak acid together, and we write the strong base as OH, and the OH pulls an H off. And this is actually a type 2. Now that we know how to write these neutralizations, we're actually ready to make a buffer. And these two substances mixed together actually do make a buffer, acetic acid and sodium and acetate. Now we're going to show that any buffer is made up of the same two components. It's always going to be a weak acid and the conjugate base of that acid. It has to be of that acid. Now, but the thing is, you might say, well, if you put acetic acid in water, you're already going to have some acetate because it does dissociate a little bit. So what are you talking about? It's true that when you dissolve acetic in water, you do get a little bit of acetate, but we're going to be talking about not the little bit of acetate that comes from that. You're going to buy a bottle of sodium or potassium acetate, which I showed there, and you are actually going to dump in way more acetate than what was there from the acid. That means you are actually adding both components, and the amount of acetate from the acid is really negligible. Now, buffers are supposed to prevent the pH from changing when you add a strong acid. So I want to see, if you add a strong acid to this buffer, is there either one of the things in the beaker that can react with the H+? And the answer is absolutely. The H+ is not going to react with acetic acid because that already has an H attached to it and it's neutral. The H+ is going to react with the base part and neutralize it. So if you want to see what happens, the H+ is going to stick to the negative ion acetate and form acetic acid. This is a type 3b neutralization, which we just finished talking about. Now when that happens, why has the H+ been neutralized or soaked up so that it won't change the pH that much? Well, you know that if H+ sticks to something, it doesn't change the pH anymore. And so H+ sticks and it's been soaked up. The reason why you choose the conjugate base of the same acid is that when the H+ sticks, you produce more of what there already was, which is acetic acid. You don't produce any new substances. All you do is make it slightly more weak acid and slightly less weak base, because every time an H sticks to the base, it's not acetate anymore. So all you've done is change the ratio of the weak acid to the weak base. You haven't put any new substances in. Now let's look at what happens if you add OH to the buffer. That won't change the pH much either, but it's going to react with the acid. It's not going to react with the negative ion, because they would repel each other, but it will react with acetic acid. And when it reacts, the OH will pull an H off to make water, and that is a type 2. The reason it's been neutralized, obviously, is that when OH takes an H+, it becomes water, and water is neither acidic or basic. And you also produced more of what was already there, which is acetate. So again, all you did was change the ratio. You took away a little bit of the acid when you pulled the H off, and you produced at the same time more of the acetate or base. So all you did was change the ratio of the weak acid to weak base. From that example, I want to give you the definition of a buffer, that a buffer is always a weak acid and the conjugate base of the same acid. So What acid can you make a buffer out of? Well, you can use any of the weak acids in the Ka table, and there are also hundreds of others. People have actually synthesized certain weak acids in organic chemistry in order to serve as buffers for different kinds of reactions when you're doing cell culture or enzyme work or all kinds of things, so that it doesn't interfere with the other processes. But these buffers are pretty much the same. You take a weak acid and the conjugate base. If you look at the Ka table, this is a really great table. It has a lot of information because you already know it's a list of weak acids, all the acids on the left of the arrows, and it is also a list of weak bases, which are the substances on the right of the arrow. And now, in addition to that, it is also a list of buffers, because anytime you mix the weak acid on the left with the conjugate base on the right, that mixture makes a buffer because that's the definition. And that also holds for the diprotic acids on the back of the table. If you look at the first carbonic acid in the table, H2CO3, if you mix H2CO3 with HCO3, it will make a buffer. But because HCO3 is amphiprotic, it can also act as an acid. And if you mix HCO3 and CO3, that is also a buffer. We're going to see, though, it's not by any means the same buffer. The pH is completely different. The other basic principle is that if you add either H plus or OH to a buffer, either one of them gets neutralized without changing the pH much, and all it does is produce the other substance. So all you do is change the ratio of the weak acid to the conjugate base, and you don't produce any new substances. One of the things I have to tell you, though, is that each of those buffers that you can make from the Ka table will not be able to buffer a solution over the entire range of possible pHs. Each buffer only works within a small range of pH. In other words, you can't make certain pH buffers out of certain weak acids. The way I want to show that is by doing an example, and I want to show you what pH acetic acid can buffer by doing a few problems, and you'll see how this works. I'm going to do a problem that we've already done, and it sounds a little weird at first, but you'll see what I'm doing. I want to calculate the pH of 0.1 molar acetic acid mixed with no sodium acetate. What am I doing? Well, obviously, I want to get the pH of the acid, and then in the next problem, we're going to add some sodium acetate and make a buffer. But let's look at the pH of the plain acetic acid first, and this is just a weak acid problem. We've already done these. These are the problems where you start with what you're given, and then you make the ICE table, ignore the x relative to the 0.1, and you end up with x squared divided by the original equals the Ka of acetic acid from the Ka table. When you solve this problem, same way we did before, multiply both sides, take the square root. The x that you get is H plus, so when you take minus the log, you get the pH. And the thing is, this is a good pH for an acid. It's 2.87, which is below 7. Now I want to turn it into a buffer. We're going to mix the 0.1 molar acetic acid with the exact same amount of sodium acetate. You don't have to use the same amount, but we're going to do that first because it's the simple case and you can see it easily. You know that sodium's going to be the spectator. Sodium is always a spectator because it makes everything soluble. So what we're really doing is mixing acetic acid and the conjugate base acetate. So the ice table is going to look different from the previous one. You're going to start with 0.1 of the acetate also. You still have no H plus initially, so you're going to shift to the right. So the plus and minus X's end up going on the same side, but this time for the acetate, you're going to end up with 0.1 plus X. Still ignore the X relative to either 0.1 minus X or 0.1 plus X. Whether it's plus or minus, it's still a very small number compared to 0.1, and we're going to find out in other chapters that you can actually ignore 2x and 3x too, because 2 times a small number is still a small number. If you plug in then the final row, you're going to be plugging in a 0.1 for acetate, but you're also plugging in a 0.1 for acetic acid, which means they're going to cancel. So what you end up with is that the X or the H plus actually equals the Ka value. And if you take minus the log of the H plus, you're also taking minus the log of the Ka. So that means that the 4.74 is the pH, but we're going to see that it's also the pKa. And the previous problem had a lower pH because when we added the acetate is a base, and when you add a base, the pH goes up. These kind of buffers that have the same amount of the acid and the base part are called equimolar, which is equal molarity. And we just got done showing that the H plus equals the Ka value. If you take minus the log of both sides, you also end up with the fact that the pH equals the pKa, because the lowercase p means minus the log. In table 2 then, which is a list of buffers, it also tells you the pH of an equimolar buffer of the two things, the one on the left and the one on the right, because the pH equals the pKa. So if you look in the table, you can see that the pH of an equimolar buffer made of acetic acid and acetate, you read across to the pKa column and you find that it's 4.74. I mentioned before that you can make buffers out of also the ones on the back of the table, the polyprotic acids. If you look at the H2CO3, you can make a buffer out of H2CO3 and HCO3. The pH of that one will be 6.38 if they're equimolar. But if you instead make a buffer out of HCO3 and CO3, the pH will be the same as the pKa, which is 10.3. So those are going to be two completely different buffers. One is acidic and one is basic, and you can't get much more different than that. A buffer is called an acidic buffer if it maintains a pH below 7. It's called a basic buffer if it maintains a pH above 7. All buffers have an acid and a base, but you call it acidic or basic based on what pH it maintains. In the next lecture, I'm going to show this by a graph, but I just want to mention the fact that for buffers, there's an effective pH range that goes about plus or minus 1 from the pKa value of the acid. Plus or minus 1, of course, means you can go up that much or down that much. For example, for an acetate acetic acid buffer, you can make a buffer anywhere in the range of 3.74 to 5.74. So if you want to make a buffer of pH 4.5 or 5, this is the perfect buffer for it. But if you want to try to make a buffer of pH 8, it's not going to work, because in order to be an effective buffer, the pH that you want has to be within that range. This is the way I present a buffer. I will usually give you both the weak acid and the weak base. although I don't have to, because if I give you one of them, you can get the other by either adding an H or taking an H off. The question about the net ionic equation for the buffer neutralizing added acid or base is, I think, the most important one to show how the buffer actually works. So let's say that you are going to add H plus to the acetic acid buffer. We've already done this, but I want to show it again. If you add H plus to the buffer, the H plus is always going to react with whatever the base part is. So since you're adding H plus, you're going to start with H plus and react it with the base. And when this happens, this is a type 3B reaction where they slap together. And the H is neutralized because it's stuck. If instead you want to write the net ionic equation for adding a base, OH, the OH is always going to react with the acid part. This is a type 2 neutralization where the OH pulls an H off the acid. And the OH is neutralized because it turns into water. You can tell what the equimolar pH will be by looking up the pKa in the acid table. And then the range that you could use for it is plus or minus 1 away from the pKa. I like to talk about where the buffering components come from, because if you were in the lab, you would have to actually measure these out. And what if you want to make an acetate buffer? What is acetic acid? What do you buy when you want acetic acid? Well, you know that 5% acetic acid is vinegar, but this bottle represents pure acetic acid. It's a liquid at room temperature, but they call it glacial acetic acid. It's the only one I know of that uses that word because it freezes just below room temperature. So if you put it in the refrigerator or outside in the wintertime, it will freeze stiff, and it looks like a glacier. That's a German word that means ice crystals. And that's the reason why they call it glacial. So if you were making a buffer, you would weigh out however much of that you needed to get the mass of acetic acid you want. The other component, the acetate, you should know this if you're going into science. You can buy just about any negative ion in the world connected to either sodium or potassium. If you go to the Fisher Scientific Catalog, I'm sure that you're going to find either one of those solids, and we have both of them in our lab. You would just weigh out how much of those you need. They're crystals. This is a visual way to imagine how adding an acid or base works. I showed those two columns, and the pink one has acetic acid in it, and the blue one has the base, acetate. The reason I picked those colors is because litmus paper is a very common way of measuring pH in the lab. You're going to use actual pH paper that has several different colors in the labs you do, but if you are using litmus in an acidic solution, litmus is pink, and in a basic solution it's blue. So that's why I did it. And you can see that if you add H plus, what you're doing is when you stick to the acetate, you take a slight amount of it away so the base goes down. You also at the same time produce the exact same amount of the acid. It's 1-to-1. This is what happens anytime you add acid to a buffer, and then you're ready to add more. The pH doesn't change that much. It's still a buffer, and it'll take more. If you add OH, the opposite happens. The acid goes down a little, the base goes up a little, and they go up by exactly the same amount, which we're going to use for a problem in the next class. This buffer is an ammonia buffer. These are used all the time in chemistry. The acid is NH4+, and the base is NH3. In the Ka table, you can see that a buffer made of NH4 plus and NH3 that's equimolar will have a pH of around 9.25, which means it's what's called a basic buffer. So for an equimolar buffer, you have 9.25, and you can make a buffer anywhere in the range 8.25 to 10.25. When a chemist thinks of a pH 9 or 10 buffer, he'll usually think of ammonia first. I always want you to be able to write the net ionic equation for the buffer neutralizing added acid. The H plus is always going to react with the base part, which in this case is NH3. This is a type 3A neutralization. The H plus sticks to the NH3, and therefore it's neutralized. The net ionic equation for adding a base to the buffer is that the OH has to react with the acid part of the buffer, which is NH4+. The OH pulls an H off of ammonium. It becomes water, so it's neutralized, and that's the net ionic. It's a type 2. You can also buy just about any positive ion in the world connected to either chloride or nitrate. The reason it's those two is that chloride and nitrate both make everything soluble. Chloride comes from sodium chloride, and nitrate is an important ion because just about any positive ion that you want to put into solution, if you dissolve the nitrate of it, it will usually, in almost every case, dissolve. Ammonia in solution is supplied in the form of a 15 molar solution. The thing about it is that ammonia is a gas, but it dissolves in water a lot, and the saturated solution is 15 molar. The problem with this one is you have to dilute it way down in order to get it to the point where it is lower concentrations. We should really do more with diluting in here, because I remember having a nursing student that was one of my students that came back from a bachelor's degree nursing program. And one of the main things you have to do in pharmacy is dilute things, both liquids and creams. And she had to take a class, but they had no classes for it. She just had to learn it all on her own and take a test before she could continue in the nursing program. And what it was she had to do all kinds of diluting problems with molarity, molality, mole fraction, mass percent, normality, and also she had to be able to do not only liquids but also creams. So she had to learn how to do what are called serial dilutions, where you dilute something 1 to 10, then you dilute it 1 to 10 again, then 1 to 10 again, and you can make it very dilute that way. I don't know what to do about that because we really don't have any time for it, but I do want to make sure that everybody understands that in medicine you are definitely going to see diluting again, because it's a really important part of pharmacy and medicine. This is a picture of the columns that have, instead of the acetate, it has ammonium in the acid column and ammonia in the base. If these are equimolar, all I want you to know is that no matter what the acid is or the base, the columns are going to look exactly alike. You add an H plus, and the acid part's going to go up a little, the base part goes down a little, and it's still a buffer. And if you add OH, it's the opposite. The acid part goes down, the base part goes up, and by exactly the same amount. The next buffer I'm going to discuss is sulfate buffer. And this one is used as a very low pH buffer. It's very convenient in chemistry. The thing is that it's got something special to look at about it, because HSO4 looks like it could be amphiprotic, but it isn't, because the conjugate acid H2SO4 is a strong acid, and you can't stick an H back onto it in water. So we need to discuss that when we talk about this sulfate buffer. I list HSO4 in the monoprotic part of the table. So sulfate is the conjugate base, and if you see on the right, on the pKa column, this is a very acidic buffer because the pKa is below 2. I also included it in the diprotic acid table as a second step of sulfuric acid because HSO4 is actually a weak acid and it has a Ka, and it of course is the same number as on the monoprotic table, but it does show that it's one of the steps of sulfuric acid. You would think that since HSO4 and H2SO4 are in the same line in the Ka table that they could make a buffer, but they can't, because HSO4 is not able to pick up an H plus in water because H2SO4 is strong and it's always 100% ions. So that means that HSO4 cannot act as the base, but it can act as the acid. So the conjugate base SO4 2- is what it makes a buffer along with. We looked up in the table that the pH when it's equimolar is equal to the pKa, which is below 2. And that means that within the buffering range, you can go all the way down to pH 1 buffer with a sulfate buffer. That's very unusual because there's not very many buffers that will go that low and still make a lot of things soluble. I just want you to know that you can buy these ions with the H still attached from chemical companies. If you look in the Fisher Scientific Catalog, you will find NaHSO4 and KHSO4, which are crystals that you can buy. And if you want to buy NaHCO3, that is baking soda. That's one with bicarbonate in it. So you can buy these. If you were going to make, if you're going to make this buffer, you would also have to have sulfate, which you can also buy as crystals. You can buy Na2SO4 or K2SO4. Why are there two sodiums? Because sulfate is -2, and when you cross down, you have to have a 2 on the metals. So what is the net ionic equation for this buffer neutralizing H+? Well, it looks like you could stick it onto either ion because they're negative, but you can't because HSO4 will not accept it. So it has to react with the base part, SO4 2-. When the H+ reacts with SO4, it sticks to it. It's a type 3b, and that's neutralized. If you add a base to the buffer, of course, it's going to react with the HSO4 because it's the only one with an H on it. So as usual, the OH turns into water, so it's neutralized, and it produces the base ion. You can make these columns that look exactly like the other two we did. If you're starting to say, why is he doing this? This is boring. That means you're getting it. Because it is boring. It's supposed to be boring. Buffers do exactly the same thing, no matter what buffer it is. The only difference is the pKa of the acid is going to determine what pH it will maintain the buffer in. This is an example of a problem, which is another way to ask equimolar. So if I ask you for a buffer with 0.31 HNO2 and 0.31 KNO2, this is another way of saying equimolar. HNO2 and NO2- are the last ones on the Ka table on page 9, and the pKa for an equimolar buffer, the pH would be 3.35. So I'm going to ask the exact same questions I asked for the others. What is the pH first? and the buffering range. We looked up the pKa, 3.35, so the range will be plus or minus 1. If you're writing the equation for the buffer neutralizing H+, the H+ will stick to the base part, NO2- and make the other component. If you add a base to the buffer, it will react with the acid part, it'll pull the H off and produce water. I call these next three questions only a chemistry teacher could think of, because what they do is they really make sure that it cements in your mind whether you understand exactly what a buffer is and how to make one. The first question is just, will these two things that you mix together make a buffer in water? And the thing is, you have to very clearly know the definition of a buffer in order to answer this. The definition of a buffer is that it has to be a weak acid and the conjugate base of the same acid. If you look at the two that I listed here, they're not going to work because they're both weak acids. There is no base, so that is not a buffer. What about NH3 and KCN? NH3 is very definitely a weak base, but so is Cn-, and I hope you're getting familiar with the fact now that K would be a spectator because it makes everything soluble, so Cn- is also a weak base. So since you have two weak bases, that will not make a buffer either. Now this one is kind of almost like a joke. I put down NaClO and NaClO2. Buffers differ by one H+, not by one oxygen. And so since these are both weak bases, both ClO and ClO2 are on the right of the arrows in the Ka table, two weak bases do not make a buffer. HCN and NaCN is a classic buffer. This is what people usually think of, that if you take a weak acid and you replace the H with an Na or K, you will get a buffer. The thing is, some people define a buffer as a weak acid and a salt of the weak acid, which is what this is. I don't like that definition because it doesn't apply to all buffers. I like a weak acid and the conjugate base of the same acid, but you have to just know what a conjugate base is. So since this is a weak acid and the conjugate base of the same acid, it does make a buffer. Since HCN and Cn- are in the same line, that verifies that it's a buffer. This one causes a problem for a lot of people, but if you look at the substance NH4NO3, the principle still holds that if NH4 is part of a salt, it is the important part in acid-base chemistry, and the other one is just going to be a spectator because NO3 comes from a strong acid, HNO3. So you can say that NH4 plus is the weak acid, NH3 is the conjugate base of the same acid, and so they should make a buffer. That's the ammonia buffer that we already talked about as an example. Since ammonium and ammonia are in the same equation in the Ka table, they make a buffer. This one is a little bit different because we're starting with a diprotic acid, but this one is really important in physiology, so I want to make sure everybody has seen this. Will you get a buffer if you mix H2CO3 and HCO3? You will get a buffer because H2CO3 is a weak acid and HCO3 is the conjugate base of that acid. H2CO3 and HCO3 are in the same line in the Ka table. The thing is that HCO3 is amphiprotic. So in the very next line, it is not acting as a base, but it's acting as an acid. So will you get a buffer if you mix HCO3 and CO3? Yes, because HCO3 is an acid and CO3 is the conjugate base. But we're going to see that even though these are both buffers, they are definitely not the same buffer. Looking at this line in the table, HCO3 and CO3 make a buffer, but it's not the same buffer as carbonic acid and HCO3 above it. The first buffer we said here will make a pH of 6 something, and bicarbonate will make and carbonate will make a buffer of 10. One's acidic and one's basic. That is very different. They're not the same buffer. And this is what it actually looks like when you put H2CO3 in water. The reason why I'm showing this is because, as you remember, H2CO3 is the way you carry CO2 back to your lungs to breathe it out. And so what you can show in analytical chemistry is that in any carbonate solution, all three of these species will all be present all the time, but one of them is always at such a low concentration that it's negligible. There's an equation that you can use to calculate this. I don't want to show you the equation and make you use it, but I will show you the graph because it's an interesting result. If you start with a very acidic solution, pH below 4, you're going to stick on both H's, and the solution's going to be almost 100% H2CO3. But if you go above pH 4, you start to pull the H, one of them, off the H2CO3, and you start to form HCO3 bicarbonate. If you add enough, they will eventually become equal. And what pH does that happen at? That happens around 6.3. That's where they intersect on the graph. They become equimolar at a pH around 10. If you continue then to raise the pH, you can pull all of the second H off, and the solution will only contain CO3 2- by itself. The thing is, this graph can tell you how CO2 exists in your blood at the pH that blood is. If you keep getting more basic, you pull more and more of the first H off, and by the time you get to about 8.5, the only thing that's present in the solution of a significant amount is HCO3 itself. And they call that a bicarbonate buffer, but really it's not a scrupulous buffer, but it acts like one, because if you go to either side of that arrow, of that bump, you get a buffer, and so it does maintain the pH. If you start to go then above that, you start to pull off the second H. So the HCO3 goes down and the carbonate goes up. Where do they cross? Your blood pH is 7.4 or so. So if you look at what's present at pH 7.4, you'll see that a little bit of it is H2CO3, but by far the most abundant one is HCO3 or bicarbonate. So your buffer in your blood is primarily H2CO3 and HCO3 that maintains it. Phosphate has a small contribution to it, and albumin, the blood protein, has a small contribution to it because there's acid and base on the surface of proteins, but those are not anywhere near as significant as the bicarbonate buffer, which comes from the dissolved CO2 coming from metabolism in your tissues. This is the reason why HCO3 or bicarbonate is one of the 4 electrolytes that they measure when you get an electrolyte profile on a blood test. These are the 4 ions that primarily get the highest concentration, so they determine the ionic strength of your blood. And those ions are sodium and potassium and chloride and bicarbonate. The other ions that are in your blood are at too low a concentration to really increase the ionic strength very much. Those are the four main ones. After we got through with all that now, I want to ask you the next one, which is a little tricky. Can you make a buffer from HCl and NaCl? It looks good because you're replacing the Na in place of the H, but it doesn't work because we said that you cannot make a buffer out of a strong acid because the negative ion will not accept H pluses, and so HCl itself cannot be a buffer with NaCl. You always have to make sure to watch whether you're being given a strong acid, because that will not make a buffer with the conjugate base. The bottom one here is another example of a kind of a classic buffer. HNO2 and KNO2, you replace the H with a K. HNO2 and NO2 minus are in the same row of the table, and therefore they make a buffer. The next question asks, what would you mix with the following to make a buffer? If you have the acid, you're going to take the H off so that you can get the conjugate base. If you have the conjugate base, you have to stick an H on so that you get the acid. In this case, NaBRO, the Na is a spectator, but the BRO minus is a weak base. So since you don't have the acid part yet, you have to mix this with HBRO to get a buffer. If you start with the weak acid HClO2, you're going to have to replace the H with something, and if you're making a buffer, you replace the H usually with an Na. You could also replace it with a K, but I always ask for the Na. So you would replace the H with an Na and you would get NaClO2. If you're starting with a diprotic acid like oxalic acid, you can't take off both H's to make a good buffer. In order to get the conjugate base of oxalic acid, you only want to take off one H. If you did mix it with C2O4 2-, it would make a buffer, but it would have one of those 3-bump profiles just like carbonic acid did, and it's harder to control the pH that way. If you only take one H off at a time, you can control the pH much better. So in order to do this absolutely correctly, you would want to replace only one H with an Na, and you would get sodium HC2O4. Now for the one I've got here, NaH2PO4, I said that there are two choices. This also confuses people, but if you look at it in the triprotic acid, phosphoric acid, you can see why I'm saying that. It's possible to mix the H2PO4 with H3PO4, which will produce a buffer, but the buffer will have a pH of around 2.12 if it's equimolar. But because H2PO4 is amphiprotic, you could also take away an H and mix it with HPO4. This one is going to have a pH around 7, so they're two very different buffers, but you can make two buffers out of H2PO4. So in order to make a buffer, you could either add an H and get H3PO4, or you could take an H away and replace it with a sodium and get Na2HPO4. But depending on which one of those you make, it will give you a very different pH. One of the very common solutions that's used for biological applications is what's called phosphate buffered saline that has sodium chloride in it also for osmotic purposes. If you make a buffer out of H3PO4 and H2PO4, you're not going to be anywhere near physiological range because the pH is going to be way too low. In order to make an appropriate buffer for physiology experiments, or even if you use it possibly as an IV to inject drugs into a person, you have to use H2PO4 and HPO4 because that's more around the pH of blood. In this question, I'm asking you to get both components of a buffer. I want you to pretend like you're a researcher in a lab, and for some reason you need to make a buffer of pH 8. Chemists and biologists need buffers of all different pHs for different purposes. So how would you go about picking an acid first? Because you have to get an acid and a conjugate base. What kind of an acid do you have to get pH 8? If you remember, the range of a buffer is plus or minus 1 from the pKa. In order to get a buffer of pH 8, you're going to have to pick a weak acid that has a pH between 7 and 9 so that it's within 1 of the pH you want. I found two acids on page 9 that would work, hypobromous and hypochlorous. The pKa's are both within the right range. I found three on the back in the diprotic table. You definitely don't want to make a buffer, though, out of hydrogen sulfide because that stuff smells like rotten eggs, and we use it in the lab when we're actually doing face-to-face labs. If you're not careful with that stuff, you can gas people out of the building in no time flat. It has to be kept under the fume hood. You can use H2PO4 and HPO4, and there's one other one I found which is at the bottom, bisulfite. I want to use this to make a point, though. We're going to use the two of them on page 9. If you put any of those 5 acids with the conjugate base, you can get a buffer that will be in the right range, but I want to use the first two. Let's suppose that you want to use hypobromous acid. Well, the pH is not 8, it's 8.68, but 8.68 only applies if you use equal amounts of them. You do not have to use equal amounts. You can use different amounts in order to adjust the pH up or down. Since this pH is higher than you want, you could use more HBRO than you do BRO minus. If you use the correct ratio of the two, you can make the buffer exactly 8.0. You can also do the same thing with HClO, except the pH of this one is below what you want. And so in this case, you would have to use more of the base part than the acid. So you would have to use more ClO minus than HClO. What we're going to do in the next class is you can't just say, I need a little bit more. You have to have a mathematical way of calculating exactly the amount of each substance you need to get a particular pH. And we're going to derive an equation to do that, and we're going to use it for a whole bunch of problems in the next class. So that will be our second lecture on buffers, the math of buffers.